Okay. Yeah. So, guys, good evening and welcome to CCNA 3. CCNA 3 is the third and the final module for CCNA. And I'll just take a brief walk away through what we will be studying in CCNA 3. So, first and foremost, this course is called Enterprise Networking, Security and Automation. In short, we call it ENSA. And it has about, I think, 14 chapters. And I'll go through the breakdown of what the chapters will involve. So first and foremost, we have single area, OSPF version 2. We learn one of the dynamic routing protocols, and OSPF is at the heart of things. So we'll talk about concept in OSPF, and then we will configure OSPF in the second chapter. Then we'll have third chapter is network security concepts, and we will get deeper into security, including VPNs and all that. Then, as part of security, in chapter 4, we'll configure access control lists. And access control list basically is a way of making the router work as a firewall by configuring statements of permit and deny the packets. Then we'll configure the SELs in chapter 5. One of the concepts we have been learning is called network address translation, how NAT has been used to slow down the process of depletion of public IPv4 addresses. And so we learn about NAT, and the system of NAT is called PAT, port address translation. And we will be able to configure it as well. Moving forward, we will talk about some WAN concept, wide area network concept, types of WAN, topologies, and all that. And very quickly, we'll move to VPNs and the IP security, virtual private network and IP security on chapter 8. And then in chapter 9, we will look at how some traffic types are always given more priority than others, and that is QoS concept, quality of service. Then we'll learn about network management as a chapter, protocols that are used for managing of networks. Then we look at how to optimize network performance in network design, chapter 11. Then one of the most important chapters in chapter 12, we will talk about how do we identify the mistakes or problems, how do we solve them? Network troubleshooting, very important. And then for, on chapter 13, we will talk about network virtualization, and we'll learn some protocols that are found within network virtualization. Virtualization is becoming a very serious thing within our network. And virtualization will come very closely with the last chapter here, network automation. Okay. And we'll see how can we be able to automate networking functions and even network devices. So this is how CCNA 3 is going to look like. It's also important for me to tell you that at the end of CCNA 3, you are going to take the final exam, and the final exam for CCNA 3 will earn you, if you pass, if it's 75% and above, it will earn you a discount voucher for taking an industrial exam. And so I will encourage you guys to work very hard, and because you only have first attempt for the final exam, and it should cost 75% and above, and you'll get the discount voucher. And the final exam, you can only do it for you to get the voucher. You can only do it after 1 month, let's say after 28 days or more. So that is something that you should be able to note. Otherwise, if you do your final exam before 28 days elapses, then you'll be given a voucher, but the voucher will be ineligible. It will not be legible for use. So I think that was something that is important for me to note. Otherwise, let's start with the first chapter here, and we are going to talk about the single area OSPF version 2 concept. And so some of the things that we expect to study here, including things like the single, we'll explain how single area OSPF operates in both networks, point-to-point network, and a broadcast multi-access network. So we'll describe some features and characteristics of OSPF. Remember, OSPF means open shortest path first. Open shortest path first. We'll describe the OSPF packet types that are used in single area OSPF. Then we'll explain how single area OSPF operates. Very, very important. And if we can understand single area OSPF, then we will definitely understand multi-area OSPF. So let's look at some features of OSPF here. Now, so OSPF is a type of protocol called a link state routing protocol. Link state routing protocol. And OSPF was developed as an alternative to replace what is called the RIP, which is another dynamic routing protocol, routing information protocol. Okay. And so OSPF is a very important protocol that we need to learn about OSPF, and we need to basically make sure that everything that we learn in OSPF should be able to make sense for us, because when the time comes for an exam, they test a lot of skills within OSPF. So OSPF was developed as an alternative for RIP, which is routing information protocol. And OSPF has some advantages over RIP, and that was why it was replacing RIP. And the first thing to note is that OSPF is more faster in terms of convergence than RIP. And because we will learn about convergence, and we'll also learn about adjacency. Okay. So OSPF is faster in achieving what is called convergence. And then OSPF can cover a very large area of the network. OSPF covers a very, very, very large area of the network. And so what I mean is that if there are routers which are found in different locations, then OSPF is actually a very good one, because it will definitely be able to, to cover a larger network. So OSPF first uses a concept of what we call areas. And in talking about areas, basically this is just a subdivision of the network into domains, into some distinct areas of control by the network administrator. So it could be department, it could be a certain branch of the network, so on and so forth. And talking about OSPF, because it is a routing, a dynamic routing protocol, every link between one router and another one, okay, is called, the state of that link is called a link state. And I think that those are some of the words we're going to hear so much, okay? So a link basically is an interface of a router connecting the router to another device, okay? So the state of that particular link is what we call a link state, right? Now, a link state information probably basically includes things like the network prefix or the network address, the prefix length or the subnet mask, and what is called a cost. And the cost here has nothing to do with money. The cost normally is just the distance to reach that particular network. Okay. So we are going to cover match and match implementation of OSPF version 2, which is for IPv4, and it will be single area, not multi-area. Now, let's talk about some components of OSPF. And the first thing I want you guys to note, is this for just a minute. Okay. Just a minute. Okay. Now, so the first thing I want you guys to note about OSPF is that just like any other dynamic routing protocol, we have EIGRP, which is Enhanced Interior Gateway Routing Protocol. We have BGP, Border Gateway Protocol. We have RIP, talked about already, Routing Information Protocol. We have ISIS, which is intermediary system to intermediary system. And then we have OSPF, which is Open Shortest Path Fast. Now, all those dynamic routing protocols I have mentioned, they have so many things in common. Okay. Number one, unlike static routing, which we did in the last bit of CCNA2, all dynamic routing protocols exchange some messages amongst themselves, amongst the routers. And that is very, very, very crucial. All the dynamic routing protocols, they exchange some messages among themselves. And why are these messages important? The messages are important because they help to build the different types of tables. We call them data structures, but they're just tables that we find in these tables. And these tables or databases, we will be talking about them soon. Then the other thing to note about all dynamic routing protocols is that all of them normally have some kind of routing algorithm, right? They have some kind of routing algorithm, and the algorithm makes several calculations to be able to do so many things, and we will talk about those in a few. Now, some of the messages that are always exchanged between the routers, the OSPF routers, we'll talk about 5 of them for now. The first one is called the hello packet. Hello packet. So the hello packet is a very, very important packet. Why? Because as we shall be learning, we learn that the hello is used to learn about new neighboring routers. Okay, what you're calling established neighbor. So discover new neighbors, new neighboring routers that are also running OSPF. And the other thing is to maintain the relationship between the routers. So establish neighbor relationship and maintain neighbor relationships. Very, very important. We will also talk about another packet or another message. We call it the database description packet. So these messages are the ones we call packets. So the hello packet, we have database description packet, we have a link state request packet, link state update packet, we have link state acknowledgement packet. Okay. So these packets are always used to do so many things. And as we are going to talk about that in a few, I want us to first talk about some databases used within OSPF. And from each database, what kind of table can we create from those databases? So number one, we have a database called the adjacency database. Adjacency database. Now, it is important to note that these adjacency databases when we talk about the word adjacent, this house is adjacent to us. Our neighbor's home is adjacent to our home. All right. So adjacent basically just means neighboring or closer to or something like that. So from an adjacency database, the tables that you can create from that database are called neighbor tables. Neighbor tables are tables that are generated from an adjacency database. How do we display the neighbor table? There's a command, and you can see it here. The command is, let me just, yeah. The command is show IP OSPF neighbor, show IP OSPF neighbor. That will display the neighbor table. The next database is called the link state database, LSDB. From the link state database, you can create a topology called, a table called topology table. Topology table is created from the link state database. Okay. Now, Apart from the linked set database, we have another database called the forwarding database. And the forwarding database, we generate the table that we know of from our previous classes. We call it the routing table. So the routing table is the table that is generated from the forwarding database. Now, how do we display the topology table? Show IP OSPF database. The topology table, show IP OSPF database. And the routing table, show IP route. We know this one. Show IP route is used to view the routing table information. Okay. Now, OSPF algorithm, the algorithm that helps OSPF to do the job is called the SPF algorithm. And SPF means shortest path first algorithm. And the guy who came up with this algorithm was called a very complex name here, DIJKSTRA, right? So there's a lot of silent letters within this name, but I always read it as Istra, because this DIJ Distra. So this is, I think this should be Distra. Distra was the name, but again, depends. So this algorithm is normally based on the cumulative cost to reach a particular network, and we will talk about that as well. So this algorithm, the SPF algorithm, normally creates a tree. A tree, all the branches are always joined to the same stem of a tree. And so OSPF creates a map or a tree of all the networks or all the distances to reach all the networks. Even if one of the networks can be reached in 10 ways, all that information will be on what is called the SPF tree. So it will place each router at the root of the tree, and then after the whole tree is calculated, then OSPF is going to use still the algorithm to calculate the shortest path to reach each and every router or each network. What is the shortest path to reach each and every network? Okay. So the SPF tree is used to calculate the best routes. Okay. And so only the best routes will be placed within the forwarding database where we create the routing table. So the routing table will only have the best routes out of the whole map. Okay. So if this is the tree, we take the tree through an algorithm to help us to create the best path through this particular network. So we might have 10 ways to reach a particular network, but the best or the shortest path to reach that network is what will be placed in the routing table. Now, this is the step of operation that OSPF uses in order to reach a state of convergence, and I'll be differentiating two words: convergence and adjacency. Convergence and adjacency. Now, to start with, let's start with adjacency. Like I told you, an adjacent building is a building closer to it. So each router must undergo a state of adjacency, which means every router must restore a relationship with the neighboring router. Any router that is closer to you must have an adjacent relationship with it. So each router must have a neighbor relationship with the neighboring router. That is adjacency. All right. If I'm having 5 neighbors, I need to know each of them. I don't care whether they have known each other, but I need to have a relationship with each of them because they're my neighbors. And that is normally the first thing. You can see the first operational state is to establish neighbor adjacencies between every 2 routers. Once the routers have established these adjacencies, then the routers now begin to exchange the state of their links, what we are calling the link state. So they'll exchange the state of their links, and like we said, this includes the network address, the subnet mask, and this network address, subnet mask, and any other information, IP address and all that. Okay. Then after they have known the state of each link, then they have to build a link state database. A link state database. So on building the link state database, which of course will be the link state database will be creating the topology tree or the OSPF tree, which has all the paths to reach all the destinations. And then this is the time when the algorithm is put in place to run through this particular tree or map so that we can only choose the best path in each and every network. Very, very important. Okay. Now, it is important to note that unlike all the other protocols, OSPF has a scalability feature, right? Because OSPF normally supports some hierarchical routing through what is called area. Now, basically, an area is a group of routers that share the same link set information within their link set databases. So an area basically group of routers which share the same state of their links in their link set databases. So OSPF can be implemented in two ways as follows. Number one, OSPF can be implemented in what is called single area. And in single area, which means all areas are in one area. And it's important that when you're using single area, it's not a must, but it is highly recommended. Always call it area 0. Area 0. Why? So that the day you want to expand your network and include more areas, it's easier because in multi-area, all the other areas must be connected to area 0. Very, very important. So what am I saying? I'm saying when you only have single area, it means all your areas are going to be in one area. All the routers must be one area. And it's preferred that we name it area 0. Because area 0 is always the backbone area. Okay? Area 0 is our backbone area. But multi-area, which is now implemented using more than one area, all areas must always connect to the backbone area. Okay? And areas that are found between one area and another one, we call it area border routers, ABR. Area border routers. Okay? And so a very good example of multi-area will actually be something like this. You can see the area 0 is here. So here. Okay. So we can see this is our area 0, call it the backbone area. And then we have area 1 to the left, area 51. Area 1 and area 51. Even if we had area 52, area 2, area 3, 4, 5, all of them must be attached to area 0, which is the backbone area. Okay. So like I said, in area 0, it's not about area 0 will be there, but we highly recommend. But in multi-area, all the routers must be in the same area. Now, what is the importance of having multi-area? What is the importance of having routers to be put in different areas? There's a lot of benefit to that. There's a lot of, there's a lot of benefits of having multi-area. One of the benefits of having multi-area, I'm just putting up my video so that we can be able to concentrate on this because this is very important. It's a concept. Now, you realize that when you have two routers connected to each other, well, let me use this example here. Let's say we only have this 4 routers. and all of them are in one area. These are 5 routers. And so these 5 routers, when they are in a single area, the only thing they need to do is they need to know each other. That means they need to exchange the state of each of their links. To realize there are very few routers, and every router will need to know the state of the links of each and every router. Now this is just 5 routers. The more and every router must also learn the routing, the networks, directly connected networks attached to every router. What if we increase it to 10 routers? What will happen? Because every router must know the state of all the other routers. Let me give you a good example. You have your phone, I have my phone, and our friend has their phone. So you have contacts, details, people's numbers and names in your phone. I have people's numbers and names in my phone, and so is the other third friend. We're asking ourselves, how can we make sure that the contacts you have that I don't have, I save them? The contacts that I have and you don't have, you need to save them. And the contact that our third friend has and we don't have, we also need to learn them. So we need to exchange this text, contact detail, so that all of us have the same number. All of us have the same number of contacts. So what do we do? So that's where the dynamic routing protocols have. In this case, every router needs to have information about all the other routers. So they need to have the same number of details within the routing table. So you realize if we are just the 3 of us, we can either decide to everyone, like for me, I need to show you my contacts and you write the name and number, number. So that is very manual and that will take a lot of time. By the time I'm done, then you have to copy mine, the other third friend have to copy theirs. So what we are saying is that instead of copying them manually, what if you just need to put your email address in my phone and you synchronize all the contacts in my email to your phone? You put for the third friend, their email, you log into your email in their phone and you do that. And then for me, I also log into your phones and I copy all the contacts. And at the end of the day, all our routing, all our contact or phone books will be having the same information because we have synchronized our emails in all our 3 phones. Now, that is what dynamic routing protocols does. In dynamic routing protocols, like I said, we want to have very small routing tables. By doing what? We are going to divide ourselves because the routers are so many. You see, the more routers you have, like I think I could give you this example. The more people, let's say we are 10 people and we need to synchronize our contacts. You realize that you will have to synchronize your contacts with the contacts from 9 other phones. And that is going to be a lot of number. All right. And so you'll have a very big phone book. So we are preventing that from happening. We are so many people, but we want to divide ourselves into different groups so that I don't have to find contacts in all the 9 people if we are 10. No, we divide ourselves into groups of maybe 3, 3, 4, 4. And the next, what we do is that we make sure that once we put ourselves in groups, we have like a class representative, or we have a team leader in each and every group. And the work of the team leader is now be able to provide leadership and act as a go-between between our group and the other group. So if we want to communicate something to the group members of the other group, we just forward the information to the team leader. We don't have to send information to all the members of that group. So in multi-area OSPF, here we also have so many routers, but we divide the routers into different groups. Okay, we have the routers into different groups, and we call those groups areas. So we have area 1, area 0, area 51. We could have area 2. But area 0 is very mandatory because area 0 must be present in multi-area. Why? Because all the areas must be connected to area 0. And so in each and every area, these are 5 routers here. We don't need to have information. We don't need to have information. A minute. Okay. You don't have to have information from all the routers. What these routers need to do, they only need to have to exchange information with the routers in this area. Okay. And these guys, area 1, they only need to exchange information with the routers in this area. They don't need to save information or the routes or the links from one area into another area, such that when you want to store information in the routing tables of each router, we just need to store information from these 5 routers. We don't need to worry about these other 5. Okay. Whenever we need to send something to this network, we just need to forward that information to R1. R1 will know what to do with it. R1, R2, remember, they're in area 0. Their work is to exchange information from one area to another area, and that's it. That's it between those areas. So we'll be having very small routing tables in multi-area, and not having information from everyone, every single router in these particular areas. And that's an advantage of, like dividing people into different small groups and having the group leader to update us about what is happening in the other group. And you know what? Wherever a problem occurs in one area of the network, that problem, it only affects the routers in that particular area. And that is very, very important to note. When a problem occurs in routers in a single area, the problem only affects the routers in that group. It can never affect routers in another area. Now, wherever there's a change in the topology, maybe one router goes down, that information doesn't need to go to all the routers in all the areas. No, that information is only exchanged within the routers that are on the same area. Okay. And wherever there are calculations, wherever there's one router down, there must be some new calculation. There must be a new SPF calculation. And so what we are saying, this SPF calculation, to avoid that frequency of every time there's a problem, multi-area will solve that problem. Multi-area will always localize the topology change in one area, and it will never need to affect routers within other areas. So there's a lot to learn from having multi-area. Now, OSPF can be implemented in either in 2 versions. This OSPF version 2 and OSPF version 3. OSPF version 2 is the implementation of OSPF using IP version 4 addresses. And OSPF version 3 is the implementation of OSPF in IPv6 addresses. Okay. OSPF version 3 is for IPv6, and OSPF version 2 is for IPv4. But they can actually run concurrently on the same router, all right? Because they'll create very different routing tables, very, very different topology tables. Yeah, so they can run concurrently within the same, because the 2 processes will be separated in the same network. Now, I talked about 5 types of messaging or packet. Hello, database description packet, DBD, link state request, LSR, link state update, LSU, and then we have link state acknowledgement, LSR. Okay. Hello, DBD, LSR, LSU, and LSR, link state acknowledgement. Now we'll talk about each of these packets. Let's start with the let me see. Just a minute. So for the link state updates, they're also divided into what is called link states advertisement, LSAs. And looking down here, so you have several types of LSAs. We have router LSAs, we have uh, uh, database synchronization LSAs, we have summary LSAs, autonomous system LSAs, multicast LSAs. So some of these, again, you will study them in CCNP, much wider. But for this particular studies, I want us to talk about Hello first. We'll also talk about the recent updates, but let's start by Hello. So one thing I tell people always is that routers work like human beings. And listen to this. How do they do that? For routers, if you are staying in a certain apartment and you have new neighbors that are relocating to stay with you in the same apartment, you see, the first thing you want to do with your neighbors, especially, you want to create a good rapport with your neighbor. Okay? You want to create a good rapport with your neighbor. And so you do that by the first thing that you want to do is you want to greet your neighbors. And from the greeting, that's where the word hello is coming. The same thing with the routers. When the routers realize there's a neighbor closer to them, and this neighbor is also running OSPF, the first thing that the routers need to do is to send a hello message to them. All right? So you send a hello message, and the neighbor will also respond with a hello. All right? So for discovering new neighbors in your locality, just like for the routers, discovering new OSPF neighbors, the routers will use the hello message. Okay? Then the hello is also used to maintain the neighbor relationship between the routers. Why? Because after every, about 3 seconds, after every, is it 3 or 10? I'll tell you guys. After every number of seconds, routers always send a hello message to their neighbor, just to know if the neighbor is still available. Okay? Just know if the neighbor is still available. It should be 10 seconds. After every 10 seconds, routers send a hello message to the neighbor to know if the neighbor is still available or not. Okay? So discovering new neighbors and establishing a relationship with them. The relationship is what we call in networking adjacency. So when you establish a neighbor adjacency, neighbor relationship. Then telling, if the router wants to tell more information to their neighbor about themselves, they want to advertise some parameters to their neighboring router, they also use hello. We'll also learn that the routers normally do some election. The routers normally carry out some election, and they like to, in terms of 3 roles, the routers can elect what is called a DR, a designated router. A DR is like a leader among the routers, can be a president, can be a class representative, it can be an MCA, can be an MP, but the routers elect a leader that they call a DR, designated router. And then they elect a deputy of the DR, we call it the BDR, backup designated router. So they elect a DR and the BDR, and the election is done using the hello packet. All right. And any router that is not a DR or a BDR will be called a DR other or DROTA. DR other or DROTA. We will talk more about that. Now, this election only happens in multi-access networks, which means mostly it is routers that are joined together using a switch. All right. We will see the topology soon enough. So any routers that are joined together using a switch, they call a multi-access network, or routers that are connected together using Ethernet cables. Then we'll also look at point-to-point networks that do not elect the DR or the BDR, point-to-point network. So we'll talk about those networks later on. But for now, let's look at some of these packets over here. Now, I need to talk about something here. I need to talk about this packet. So we already talked about hello, establish neighbor, new neighbor relationships, and maintain those relationships and do election of the DR and PDR. Database description packet. Remember, once you have a neighbor living in your locality, you start knowing a little bit of information about your neighbor as you also reveal more information about you to your neighbor. For example, you start knowing where do they go to work, where do they go to church or to the mosque, where do they, for example, where do they, which banks do they use, for example, which road do they use, where do they go for shopping, for example, just so on. Where do they come from? What is their village or something like that? Are they Kenyans or they are not? So all that information that you exchange with your neighbor and the neighbor exchanges with you, in OSPF, we call it a database description, okay? You get to store a database that describes your neighbor, something like that. I want you to relate this to human relationships, and because this is how normally routers work. So we have a database description packet, a packet that stores a whole database of what the routers are. Now, once you have a database that stores records about your neighbor, but you feel that you still need some more information. For example, you need to know, maybe one day you lost your identity card or your identity document, and you need to know that your neighbor works at one of the government parastatals that deals with, uh, the production of these government identification documents. For example, it might be your passport or it can be your identity card. Okay, only for you to realize that your neighbor is actually a senior person there. So you just go on to inquire from them. And so if you ever need more information, once you have the database description, the routers use another messaging called the LSR, link set request. And so the link set request is actually used to exchange more information, right? To request for more information from the other neighbor. And when you send a request to your neighbor, the neighbor gives you an update of that request. So that's when now we have another messaging called the link set update, which is always it's the update, of course, brings information that was requested for using the link set request. Okay, and so if you request something from your neighbor sends you an update, and when your neighbor sends you an update, you're gonna have to say thank you, and that's why we have the last message, which is called link set acknowledgement. You have to acknowledge. All right. So hello, get to know your neighbor. Know more information about your neighbor using database description. You need any more information, use the link set request. If you get a link set request from your neighbor, you must send a link set update, and the neighbor must say thank you by sending a link set acknowledgement. Now, that is going to become very important as we look at the operational states of OSPF. From the moment you turn on OSPF in a router, or you activate it, or you enable it, until the routers, one, they maintain a relation with their neighbors, which we call a neighbor adjacency. Two, until when all the routers have learned about all the routers, which means every router in the domain or in the area has information from all the routers in that area. We call that a set of convergence. So there's adjacency between any two routers and convergence among all the routers, right? So these are some of the operation states that the routers go through from the beginning to the end. Number one, we have a state called the down state. And when a router is at the down state, it is not receiving any hello message. In fact, the OSPF is down at this point. It is, even though it is not receiving any hello messages, it's actually sending some hello packets to other routers. Okay. Then at this point, the router goes to the next state, which is called the init state. So that is the second state. So at the init state, hello packets are now being received from the neighbor. All right. And listen to this. The router has learned something from the neighbor. the router has learned an identity of their neighbor, and we call this a router ID, router identification. By the way, each router must have a unique ID, and that ID is what we call the router ID. And the hello packets that are being received are now having the router ID of their other router neighbors. After they know the router ID, the router now proceeds to the third state, which is called the two-way state. And how crucial this state is. One, at the two-way state, it means, of course, there's bi-directional communication. Both routers are now communicating in two-way. And for routers that are in what is called a multi-access network, which means these routers are connected using an Ethernet cable, or the routers are joined together with a switch. This is the stage where an election will happen. Election of the DR and the BDR. Okay. And after this election, the router moves to the next state, which is called the exstart state. Exstart state. For exstart state, here now, the routers that are connected with a type of connection called the point-to-point network, they will decide which router will initiate the process of exchanging the second packet, which is called the database description packet, DBD packets. So they are going to decide which router will initiate the process, okay? And they decide upon the initial DBD packet with this number. Then at this point, the routers move to the next stage, which is called the exchange state. From exstart, we go to exchange state. Here now, the routers have decided which router will initiate, so they begin to exchange the database description packets now. Now listen to this. If the router needs any additional information, like I told you, then and only then should the router move to the loading state. All right. If the router needs any more information, they need to move to the next state, which is the loading state. And at the loading state, of course, this exchange of the link set request, and the router will get a link set update. Okay. And of course, send acknowledgement. So from the exchange state, you only move to the loading state if you need more information. Otherwise, if the router doesn't need any information, the router will move straight from exchange state to full state. And at the full state, this is where we've reached a state of convergence. All the routers have now synchronized, they have converged and known about all the other routers within the network. So this state's very, very important. Now, like I'd mentioned to you, that normally the routers exchange hello packet to establish this adjacency. The hello packets are always exchanged using multicast addresses. So a multicast address, an example. Remember, this is the address used for one-to-many, not one-to-all, one-to-many. So the address used here is always the 224.0.0.5, and this is the address that is used for OSPF to send this packet. Okay. So, like I told you, that the router ID is used to uniquely identify each router within an OSPF domain. And the router ID, because we are going to configure it, it just looks like any other IP address, right? It also has that 2 bits, like any other IPv4 address always has that 2 bits. Okay. So it's a big deal, router ID, and I'll be showing you soon enough that if you don't configure the router ID, the router has a way of creating its own router ID, and I'll take you through those processes. Okay. Now, this is an example of a multi-access network. You realize that this is a network where routers have been connected together using a switch. See? Switch here in the middle. Okay. And so you realize that every router in this topology must establish an adjacency with every link or with every router. Okay. So I need us to count here because I want to explain something. How many routers are we having? We have 5 routers. Now, if each router must have a relationship with every router, which means this router must have a relationship with this guy, this router must have a relation with this router, this router must have a relation with this router, this router must have a relation with this router, this router must have a relation with this router, this router must have a relation with this router, this router must have a relation with this router, this router must have a relation with this router, this router must also have a relation with this router. So to explain the number of relations you can see, we call them adjacencies. How do we know the number of adjacencies given a certain number of routers? So to know the number of adjacencies, if someone tells you calculate the number of adjacencies, it's a very simple formula here. N minus 1. So n into n minus 1, and everything divided by 2. Okay? N into n minus 1, everything over 2. So where n is the number of routers. For example, if you have 5 routers here, we'll have 5 into 5 minus 1 over 2. Okay? You know 5 minus 1 is 4. 4 times 5 is 20. And 20 divided by 2 is actually 10 adjacent. Okay? So now, to prevent, you know, this is just 5 routers. What if we have 10 routers? Where we'll have 5 into 5 minus 1 over 2. You know, 5 minus 1 is 4. 4 times 5 is 20. 20 divided by 2 is 10. No, I didn't do it well. I'm talking about 10 routers. Sorry, not 5. 10 into 10 minus 1 over 2. So 10 minus 1 is 9. 9 times 10 is 90. 90 divided by 2 is 45. 45. If we place n by 10. So the more routers you have, the more adjacencies you'll be creating. Look at 5 routers give us 10 adjacencies. I've doubled the number of routers to 10. And we have 45 adjacencies that will have to be made. And that is a problem. Why is it a problem? Because the exchange of these hello messages among the routers to establish these neighbor relationships we call adjacency uses a lot of bandwidth. And we don't want this to happen. Okay? And that is why, to help us to manage this, let me just display a certain, yeah. To help us to manage this adjacency, I want you to look at a certain, yeah, this is when we are creating the 5 adjacencies. What if we don't want to have those many adjacencies? Okay? Let me give you a very practical example. So here it is. You are in a class of let's say 20 students. Okay, and then the first day you're in class, and you need to know each other. You see, you're meeting the class for the first time. None of you knows about the other. So it's like everyone must approach every student in the class among the 20. You tell them your name, and they tell you your name. Go to student 1. You go to student 2, tell them your name, and they tell you their name. So until you reach the 19th student, because you are the 20th. So if everyone does this, you know, that is a total waste of time. But we are saying, what if all of you tell the teacher your names, or the teacher has a list of your names, and the teacher stands in front of the class and reads your names aloud and tells you, this one is called Mark, this is called Peter, this is called David, this is called Mercy, this is called Leonida, this is called Joseph, so on and so forth. All right. You see, that's going to save time, because it will save you from going to meet everyone, because the teacher, all of you just have to send to the teacher your names, and the teacher is going to reach out that message to everyone else in the class. So like I told you, I relate OSPF a lot with human being and how human beings interact. And so that's the same thing with OSPF here. OSPF, it has to create so many of those adjacencies. We have seen that. It is going to create chaos in the network because it is going to use more bandwidth, which is supposed to use to forward your emails and your WhatsApp messages and your web browsing traffic. So instead of using the bandwidth for doing some productive work, it is going to use the bandwidth to exchange hello messages. And every time hello is sent, it has to be acknowledged. Okay. And every time it is acknowledged, I mean, there might be some request, ls listed request and listed update. Okay. And so to prevent the exchange of so many of these packets there, we are going to do an election among the routers. We'll elect a DR and a BDR. It's like the class rep and the assistant class rep, or the president and his deputy, so that the DR, which is the designated router, is always the one in control. So what we do, the DR will be like the teacher in class or the class rep in class, so that we send all our queries to the class rep. Then the class rep is going to communicate to everyone else in class. Meanwhile, the deputy class rep is waiting when the class rep is not there, or when the class rep is sick. It actually takes over and does the work of the class representative or the class secretary. So let's see what happens. R2, okay. So you can see everyone is generated RSAs here. Everyone is exchanging messages here. And so this is creating chaos in the network. This is when we have not done the election yet. Anyone wants to tell everyone, this is my name, I'm R3 or R1, and this is my phone number, or this is where I come from. You see, this is creating more chaos, and this one uses more bandwidth in the network. Okay. What if we could prevent this? Okay. What if we will just elect the DR and the BDR so that everyone doesn't need to talk to everyone? We just need to talk to the DR and a copy sent to the BDR, and the DR will now be able to communicate to everyone else. Okay, look at this. If I need to communicate to everyone, I send my information to the DR, and a copy will be sent to the deputy or backup DR. And the DR's responsibility is now to send that information to everyone else in the network. That will be much faster than letting everyone talk to everyone in the network. All right, letting everyone talk to everyone in the network. So R2 forwards to everyone. Okay. Then R3 talks to everyone, and R1 talks to everyone, R5 talks to everyone, R4 talks. Look at how messy and chaotic this one is. Okay. It takes up more bandwidth than usual. So this is why we need to elect one of the routers to become a DR and another one become the BDR to always make work easier for us. And that is going to help us to do what? It will help us to create, prevent this flooding of LSS. We'll just need to elect a DR to prevent the flooding of those messages and increase the, help us to prevent the usage of more bandwidth within the network. Okay, so that the DR receives it and the BDR receives a copy, but the DR communicates to everyone in the network. Now, the DR becomes the collection point of all the messages. We call them the listed advertisements. They are sent and they are received. But we elect a BDR wherever the DR fails. And like I told you, any other router that is not the DR or the BDR, we call it the DROTA or DR other. DR other, okay? It is neither the DR or the BDR, right? Now, so that is very, very important. And that is, the end of that. I want us now to look at a little bit of implementation of DR. we won't finish it. We will continue from there tomorrow, because OSPF can be a very long chapter sometimes. So